Everything your physics teacher told you about the speed of light being an absolute limit is a lie. Scientists are quietly taking it apart. Faster than light travel is no longer a fantasy, it is a physics problem, and we are this close to solving it. And today, we are going to walk through all of it together. Where this idea came from, what the laws of physics actually say, and what they leave open. If you are ready to discover why the universe does not forbid faster than light travel, make sure to subscribe to this channel and give this video a like. Now let's begin. Every single discussion about faster than light travel starts in the same place. It starts with a man, a patent office in Bern, Switzerland, and a thought experiment about riding a beam of light. In 1905, a 26-year-old physicist named Albert Einstein published a paper that would permanently change the way humanity understands reality. His special theory of relativity introduced the world to an idea so strange, so counterintuitive, and yet so perfectly supported by mathematics that it has never been seriously disproven in over a century of testing. The speed of light in a vacuum is a constant. It is always approximately 299,792,458 meters per second, and nothing that has mass, no particle, no ship, no signal, can reach it. Not because we lack the technology, but because the math itself breaks down. Here is why. As any object with mass moves faster, it requires more and more energy to keep accelerating, not just a little more, dramatically more. The closer you get to the speed of light, the more energy you need, and the math shows that to actually reach light speed, you would need an infinite amount of energy. That is not a practical problem, that is a fundamental one. You cannot gather infinite energy. There is no fuel tank big enough, there is no engine powerful enough. The universe, according to Einstein, set a speed limit, and it made that limit physically impossible to break, not just difficult. For most of the 20th century, scientists accepted this, and honestly, they had good reason to. Every experiment ever conducted confirmed Einstein's predictions. Particles accelerated in machines like the Large Hadron Collider at CERN in Geneva get closer and closer to the speed of light the more energy you pour into them, but they never reach it. Never. Neutrinos, the ghostly particles that pass through entire planets without stopping, travel at speeds so close to light that the difference is almost unmeasurable. But even they fall just short. In 2011, a team at CERN briefly thought they had found neutrinos moving faster than light. The world's media exploded. Scientists were stunned. But within months, the culprit was found. A loose fiber optic cable in the timing equipment had introduced a tiny error. The neutrinos were not faster than light after all. Einstein was right again. So if Einstein's speed limit is so airtight, why are serious physicists still working on faster than light travel? Why are universities publishing papers on warp drives? Why is this conversation happening at all? Because Einstein himself left a door open, and most people never noticed. Here is the thing that changes everything, and it is the heart of what this entire video is about. Einstein's special relativity, the theory with the speed limit, applies to objects moving through space. But in 1915, Einstein published an even more powerful theory, general relativity. And general relativity is not about how fast things move through space, it is about how space itself moves. And here is the stunning part. The universe has no speed limit for the expansion or contraction of space. None. We know this is true because we can observe it. Right now, today, galaxies at the edge of the observable universe are moving away from us faster than the speed of light. Not because they are breaking any rule, but because the space between us and them is expanding. Space itself is stretching. And Einstein never said space had to follow the same rules as the things inside it. That single realization, that space can move faster than light, even when the objects inside space cannot, is the crack in the wall. It is the loophole. It is the door. And in 1994, a Mexican theoretical physicist named Miguel Alcubierre walked through it. Alcubierre's idea was elegant in a way that only the best physics ideas are. What if, instead of trying to push a spaceship faster than light through space, which Einstein says you cannot do, you let the spaceship sit perfectly still inside a bubble, and you moved the bubble instead? You would compress the space-time in front of the bubble, shortening the distance ahead, and you would expand the space-time behind it, stretching the distance behind. The spaceship inside the bubble would never technically exceed the local speed of light. It would be stationary relative to its immediate surroundings. But relative to the rest of the universe, the bubble and everything in it could move arbitrarily fast, faster than light, much faster, all without breaking Einstein's rules. This concept became known as the Alcubierre drive. And when physicists first read the paper, many of them felt something rare in science. Genuine, almost childlike excitement. It was mathematically consistent. It did not violate general relativity. It was not magic, it was geometry. The idea was not to go faster than light. The idea was to make the distance shorter. But here is where the excitement of 1994 ran headfirst into a brutal problem, and where the story of faster-than-light travel gets even more fascinating. Alcubierre's warp bubble worked beautifully on paper, but to create it, the equations demanded something that at the time was considered completely impossible: negative energy. Not just a little bit of it. Exotic matter with negative energy density, a substance that, as far as anyone knew, did not exist anywhere in the universe. Normal matter, the stuff everything is made of, your body, the air around you, the planet beneath your feet, has positive energy. Negative energy is the opposite. It behaves in ways that feel almost supernatural. It would push when you expect it to pull. It would have what physicists call negative mass. And as far as any experiment has ever shown, nothing like that has ever been found. So Alcubierre's idea sat in that strange limbo that many brilliant physics proposals occupy. Theoretically beautiful, practically impossible. It was discussed in journals, debated at conferences, and quietly filed away under fascinating but unreachable. For years, the warp drive was the kind of idea that serious scientists found interesting to think about, but not something that felt like real science. Then, slowly, things began to change. And when they changed in ways that nobody expected. Miguel Alcubierre, back in 1994, handed the world a theoretically sound blueprint for a faster-than-light drive. The math worked. General relativity allowed it. The geometry was elegant. But the engine required something the universe did not seem to offer: exotic matter with negative energy density. And for years, that requirement acted like a locked gate on the entire concept. You could see the road ahead, you just could not get through the door. But science has a funny way of dealing with locked doors. It does not always knock. Sometimes it finds a window, sometimes it rebuilds the door entirely. And in the years that followed Alcubierre's original paper, a quiet but determined group of researchers began doing exactly that, chipping away at the problem, one equation at a time, looking for a version of the warp drive that did not require the impossible. Let us talk about what they found, because what they found is genuinely remarkable. The first major crack in the exotic matter problem came from a physicist named Harold White. White was not working at some fringe institution. He was at NASA's Johnson Space Center in Houston, Texas, one of the most respected space agencies on the planet. In 2012, White presented findings at a conference that sent a ripple through the physics community. He had been re-examining Alcubierre's original equations, and he noticed something that others had overlooked. The original design called for a warp bubble that was essentially a flat ring around the spacecraft. But White found that if you changed the shape, if you made the bubble oscillate, if you varied its thickness and let it vibrate dynamically rather than staying rigid, the amount of exotic matter required dropped dramatically, not by a little, by enormous, almost unbelievable amounts. Alcubierre's original calculations suggested you would need a mass of exotic matter roughly equivalent to the planet Jupiter, to power the drive. White's modifications brought that number down to something closer to the mass of a spacecraft itself, or even less. He also proposed a small-scale laboratory experiment called the White-Jude warp field interferometer to look for the tiniest possible distortion of spacetime using laser interferometry, not to build a warp drive, just to see if spacetime could be nudged, even slightly, by the right configuration of energy. The experiment was modest in scale, but the ambition behind it was enormous. It was the first serious attempt to test warp field physics in a laboratory setting. Now, to be precise and honest with you, as this channel always will be, White's experimental results were not conclusive. The interferometer did not produce clear evidence of a warp field. There were questions about whether the signals detected were genuine spacetime distortions or simply noise from the environment. White himself acknowledged the limitations. But here is the important thing: the willingness of a NASA scientist to pursue this seriously, to bring it into a real laboratory, to subject it to real experimental scrutiny, that shifted something in the scientific culture around warp drives. It said, this is a legitimate area of inquiry, these are questions worth asking, and once that door opened, others walked through it. In 2020, a physicist named Erich Lentz at the University of Göttingen in Germany published a paper that caused serious excitement in the theoretical physics world. Lentz had been working on a different approach to the warp drive problem, and he found something that Alcubierre and White had not. He discovered a class of warp drive solutions that used what physicists call solitons, self-reinforcing wave patterns, to create the warp bubble. And crucially, his solutions did not require negative energy at all. Every single source of energy in his model was positive, normal energy, the kind that actually exists in the universe. Read that again, because it matters. A theoretical physicist found a mathematical solution for a warp drive using only forms of energy that we know exist. Lentz was careful not to oversell this. He made clear that the energy densities required were still far beyond anything humanity could currently produce. We are talking about energy scales that dwarf entire stars. But the conceptual barrier had shifted. The argument was no longer, you need something that cannot exist. It became, you need something that exists but that we cannot yet harness. That is a completely different kind of problem. One is a wall, the other is a mountain. Walls cannot be climbed, mountains can. Then came 2021 when researchers at the think tank Applied Physics, led by Alexei Bobrik and Gianni Martir, published a comprehensive framework paper in the journal Classical and Quantum Gravity. This paper did something that had never quite been done before. It organized all known warp drive concepts into a single taxonomy, a map of the entire landscape of warp drive physics. And in doing so, Bobrik and Martir demonstrated something profound, that there existed a broad class of warp drive geometries that did not violate the known energy conditions of physics. These were called positive energy warp drives. And while they were subluminal, meaning they could not yet exceed the speed of light, they represented the first fully physically consistent warp drive models in history. You heard that right. Fully physically consistent, no exotic matter, no negative energy, no violations of known physics, just space-time geometry, dense ordinary matter, and mathematics. Speaking of crossing enormous distances, Ocean, this connects directly to what we are discussing. You might want to check out another video on this channel called How Long Would It Take Us to Travel 1 Light Year Nowadays? It puts the raw scale of interstellar distances into perspective using our current best technology. Once you see those numbers, you will understand exactly why the warp drive conversation is not just an intellectual exercise. The link is in the description. Back to our story. By 2024, the pace of serious warp drive research had accelerated in ways that felt almost surreal. Jared Fuchs, Christopher Helmerich, and their colleagues at the Advanced Propulsion Laboratory at Applied Physics, along with researchers from the University of Alabama in Huntsville, and from the Technion in Israel, published what became one of the most discussed papers in recent theoretical astrophysics. Their work, titled Constant Velocity Physical Warp Drive Solution, presented a subluminal warp drive model that satisfied all energy conditions simultaneously. All of them. This was not a partial solution or an approximation. It was a complete, self-consistent warp drive, space-time geometry built using only positive energy. The paper confirmed numerically that the shift vector distribution, the mathematical fingerprint of the warp bubble, could not be reduced to a simple coordinate transformation. In plain language, this was a real space-time effect, not a mathematical trick, not an artifact of the coordinate system. An actual physical distortion of space described by general relativity, achieved without exotic matter. Now let us be clear, because intellectual honesty is everything on this channel. The warp drive in this paper was subluminal. It could not exceed the speed of light. The researchers themselves acknowledged this openly. The speeds involved were not going to get you to the nearest star system in a reasonable time frame. But, and this is the crucial point, and this research proved something that physicists had spent 30 years doubting, that a physical, energy condition respecting warp drive solution actually exists within the framework of general relativity. The exotic matter barrier, the thing that had defined the conversation since 1994, had been broken at the conceptual level, and then December of 2025 arrived, and the conversation changed again. A new paper, published and widely covered by outlets including Popular Mechanics, described what researchers called a fully physically realized model for a warp drive, one that built on the positive energy framework but pushed its mathematical foundations further. The paper worked through the geometry in what physicists call ADM formalism, a way of slicing space-time into layers and analyzing how each layer evolves. It addressed one of the oldest and most serious objections to warp drives, the causality problem, the worry that a faster-than-light bubble could, in principle, be used to violate the flow of cause and effect, to, in some sense, travel backward in time. The new work introduced what the authors called a hyperbolic regularization, a mathematical technique that restored what physicists call finite characteristic speeds to the warp drive geometry. In plain English, they found a way to make the warp bubble causally consistent, to make it play nicely with the arrow of time. This did not solve every problem, it did not hand us a working engine, but it removed one more item from the list of fundamental objections. And in science, that is how revolutions happen, not in one dramatic moment, but in a long series of obstacles being removed, one by one, until one day you look back and realize the path is clear. Here is what this whole progression tells us, and why it should matter to you personally. We are witnessing in real time the transformation of an idea from science fiction into science. Alcubierre gave us the concept in 1994. For most of the following 2 decades, it lived in the margins. Interesting, but considered impractical. Then White brought it into a NASA lab. Lentz removed the negative energy requirement. Bobrick and Martyr built a complete positive energy framework. Fuchs and his team constructed a fully consistent physical solution, and the papers published in 2025 pushed the mathematical foundations even further towards something that could, one distant day, be engineered. Each of these steps happened because individual human beings, curious, stubborn, unwilling to accept impossible as a final answer, sat down with a pencil or a computer or a chalkboard and asked, what if? What if we look at this from a different angle? What if the problem is not the destination but the approach? That spirit, that refusal to stop asking, is the most human thing in science. And it is the same spirit that 40,000 years ago made our ancestors look up at those same stars and wonder what they were. We are made of stardust, every atom of carbon in your body forged in the furnace of a star that died before our sun was born. And now those atoms, arranged into curious, restless, brilliant human beings, are trying to find a way to go back, to cross the void, to visit the source. That is not just physics, that is poetry. But we are getting ahead of ourselves, because before we talk about where warp drive research goes from here, we need to understand something that most popular science coverage completely skips over. We need to understand why the exotic matter problem was so hard in the first place, and what recent physics tells us about whether exotic energy is truly impossible or just something we have not learned to handle yet, because the answer to that question will surprise you, and it will take us somewhere even more unexpected, into the quantum world, where the rules of reality get genuinely strange. Let us take a step back from spaceships and equations for a moment. Let us talk about something that sounds almost like a magic trick, but is completely, rigorously, experimentally real. Empty space is not empty. Read that again. Sit with it for a second, because everything you have ever been told about a vacuum, about the void between stars, about the nothing between atoms, is only half the story. Quantum physics, the branch of science that describes the behavior of the universe at its smallest scales, tells us something deeply strange and deeply beautiful. Even in a region of space with absolutely nothing in it, no atoms, no light, no particles of any kind, there is still energy. A constant, restless, shimmering hum of activity at the quantum level that physicists call zero-point energy, or vacuum energy. And that energy, it turns out, is not just a theoretical curiosity. It is real, it is measurable, and it has implications for the future of faster-than-light travel that most people have never heard about. To understand why this matters, we need to go back to 1948. A Dutch physicist named Hendrik Casimir was thinking about something that might seem completely unrelated. Two perfectly smooth, uncharged metal plates placed extremely close together in a vacuum. No charge, no force acting between them in any classical sense. By every ordinary expectation, they should just sit there, doing nothing. But Casimir predicted something astonishing. He said that the quantum vacuum between those two plates would behave differently from the quantum vacuum outside them. The plates would restrict which quantum fluctuations, or which virtual particles popping in and out of existence, could fit in the gap between them. Outside the plates, all fluctuations were free to exist. Between the plates, only the smaller ones could fit. That imbalance would create a pressure difference, and that pressure difference would push the plates together, measurably, detectably, with a force that could be calculated precisely. That force is called the Casimir effect. And when physicists actually tested it in the lab, it was exactly where Casimir said it would be, to within a fraction of a percent. You can go into a laboratory today and put two metal plates close enough together. We are talking about gaps smaller than a single micrometer, which is 1/1,000,000th of a meter, and you will feel them snap toward each other because of quantum vacuum fluctuations. Not gravity, not electrical charge. The energy of empty space itself pulling them together. Now here is where this connects to the faster-than-light story. Remember the problem with Alcubierre's original warp drive, the need for negative energy density, for energy that is, in some sense, below zero? For decades, physicists assumed that was impossible because in the everyday world, energy is always positive. You cannot have less energy than nothing. But quantum mechanics does not play by everyday rules. And what the Casimir effect proves, not hypothetically but experimentally in real laboratories, is that there exist regions of space where the energy density is genuinely lower than that of the surrounding quantum vacuum, lower than empty space. In the precise technical sense that matters for warp drive physics, that is negative energy density. Let that sink in. Negative energy density, the very thing that Alcubierre's original equations called for, is not just a theoretical fantasy. It is something that happens between two metal plates in a university laboratory. It is real, it is small, it is incredibly small in fact, nowhere near the magnitudes that a warp drive would require, but the principle is established, the universe allows it, And that changes the conversation entirely. There is a physicist named Steve Lamoureux who, in 1997, performed the first precise direct measurement of the Casimir force at the University of Washington. His experiment confirmed Casimir's 49-year-old prediction to within 5% accuracy. Later experiments, including those using sophisticated microelectromechanical systems, have confirmed the effect to within 1% or less. The Casimir effect is not a fringe idea. It appears regularly in the pages of Nature, physical review letters, and some of the most respected scientific journals in the world. It is taught in graduate physics courses. It is considered in the engineering of nanoscale devices, where it can actually become a significant and sometimes problematic force. But the quantum vacuum holds even stranger gifts than the Casimir effect. In 2023, experimental physicists confirmed something that had been theoretically proposed all the way back in 2008 by a Japanese physicist named Masahiro Hotta at Tohoku University. The protocol is called quantum energy teleportation. And while the name sounds like pure science fiction, the concept is firmly grounded in quantum information theory. The idea works like this. In a quantum vacuum, different regions of space are not truly independent. They are entangled, connected in a subtle quantum way, even across distances. Hotta showed theoretically that by making a precise quantum measurement in one location and then sending classical information about that measurement to a distant location, a second observer could use that information to extract energy from the vacuum at their location. They would not be creating energy, they would be borrowing it, taking advantage of the correlations built into the vacuum itself. In 2023, two independent experimental teams, one using quantum computers at IBM, another using quantum devices at different institutions, actually demonstrated this protocol working. They extracted small but real amounts of energy from the quantum vacuum using entanglement correlations. Quantum magazine covered it in detail. The physics community was fascinated, not because the energy extracted was large, it was tiny, on the scale of quantum computers, but because it demonstrated that the quantum vacuum is not just a passive backdrop to reality. It is an active, interconnected energy landscape that can, under the right conditions, be manipulated. Now, a very important clarification, because this channel does not exaggerate and does not mislead. None of this means we are about to build a warp drive. The negative energy regions created by the Casimir effect are so small that scaling them up to the magnitudes required for even a microscopic warp field would require technologies we cannot currently imagine. The energy extracted through quantum energy teleportation, while real, is on scales of individual quantum bits, not anywhere near engineering scales. And physicists like Ford and Roman have shown that quantum mechanics itself imposes limits, called quantum inequalities, on how much negative energy you can concentrate in one place and for how long. The universe, it seems, is generous enough to allow negative energy, but not so generous as to let you accumulate it without restriction. But here is the thing about quantum inequalities that most people do not appreciate. They do not say negative energy is impossible, they say it is bounded. They say it obeys rules, and rules in science are not obstacles, they are instructions. When you know the rules of a system, you know exactly what you need to do to work within them. You know what geometry, what configuration, what approach gives you the most negative energy density for the least cost. And that is precisely what a new generation of physicists is working on right now, finding the optimal shapes, the most efficient configurations, the cleverest arrangements of matter and energy fields that extract the maximum possible negative energy from the quantum vacuum while staying within the boundaries that quantum mechanics permits. A 2025 paper from Johns Hopkins University, authored by Daniel Zachary, proposed something genuinely creative in this space. He explored whether quantum energy teleportation combined with Casimir-enhanced confinement could generate measurable spacetime curvature, a detectable bending of space using equipment that could realistically be built in a laboratory. He proposed specific experimental setups using atomic clocks, optical interferometers, and optomechanical devices to detect the curvature. He introduced what he called the quantum curvature compression channel, a speculative but mathematically grounded framework for achieving apparent geodesic compression, a kind of apparent shortening of distance through synchronized quantum energy operations. It is not a warp drive, but it is potentially a laboratory-scale precursor to the same physics that a warp drive would use. This is how science advances, not in one enormous leap, but in 1,000 small steps, each one extending the reach of the previous. In 1903, the Wright brothers flew 120 feet at Kitty Hawk. 66 years later, 66 years, human beings walked on the moon from 120 feet to 240,000 miles. That is what persistent, curious, fearless scientific inquiry looks like across generations. We are perhaps at our Kitty Hawk moment for warp physics. We are not yet flying, we are barely off the ground, but we have demonstrated in real laboratories that the key ingredient, negative energy density, actually exists in nature. We have shown that the quantum vacuum can be manipulated. We have found that the theoretical barriers to a physically consistent warp drive are not absolute. We have built mathematical models that satisfy all the known energy conditions of physics. And we have started designing experiments to probe the boundary between quantum mechanics and space-time geometry. And here is what makes all of this even more breathtaking when you zoom out and look at the big picture. The same quantum vacuum that might one day power a warp drive is the same quantum vacuum that fills every cubic centimeter of space in the entire observable universe. It is there in the void between galaxies. It is there in the space between the nucleus of an atom and its electrons. It is there in the room where you are sitting right now, buzzing invisibly with an energy that we are only beginning to understand. You are not surrounded by emptiness. You are immersed in something alive, something connected, something that quantum mechanics is slowly teaching us to read. We are made of stardust, yes, but we live inside a quantum ocean, and we are just beginning to learn how to swim. There is, however, one enormous obstacle we have not fully confronted yet. We have talked about Alcubierre's geometry, about positive energy solutions, about the Casimir effect and quantum vacuum energy. But there is a problem that stands between all of that beautiful physics and an actual functioning warp drive, a problem so deep and so strange that it touches on some of the most fundamental questions in all of physics. It is the problem of control, of causality, of whether the universe will even allow a warp drive to be turned on and off without tearing something in the fabric of reality. And when you hear what physicists have actually found about this, about what happens at the edges of the warp bubble, about what the math reveals when you ask how you would steer it, stop it, or start it, you will realize that the universe, in its infinite complexity, does not make anything easy, but it also does not make anything impossible without a fight. The causality problem with warp drives is one of the most fascinating puzzles in modern physics, and it leads us directly to a concept that is even stranger than faster-than-light travel itself, the possibility that a warp drive, in the wrong hands or under the wrong conditions, could theoretically be used as a time machine. Time is the most personal thing in the universe. You feel it every single day, in the way a morning moves slowly when you are bored, and vanishes instantly when you are happy, in the way a year feels short looking back but endless looking forward. Time is the river you live in. You cannot step out of it. You cannot slow it down. You cannot reverse it, or so it seems. But here is something that should genuinely unsettle you in the best possible way. The thing you call time, that steady, reliable, one-directional flow from past to present to future, is not what physicists think it is. And the deeper you go into the equations of general relativity, the stranger time becomes. Because general relativity does not treat time as a universal constant. It treats time as a dimension, a flexible, bendable, warpable dimension that responds to mass, to energy, to the curvature of space-time itself. Time runs slower near massive objects. Time runs faster in open space. Two identical clocks, one on the surface of the Earth and one orbiting in a satellite, will tick at different rates. This is not philosophy, it is engineering. The GPS satellites above your head right now have their clocks corrected every single day to account for relativistic time dilation. Without those corrections, your GPS would drift by kilometers within hours. So time is already weird, it is already flexible. It is already something that bends under the right conditions. And when you introduce a warp drive into this picture, a bubble of distorted space-time moving faster than light through the universe, the weirdness escalates dramatically. Here is the heart of the causality problem with warp drives explained as clearly as it can be. In ordinary physics, cause always precedes effect. You light a match, then the paper burns. You throw a ball, then it lands. The arrow of time flows in one direction, forward, and every event in the universe respects that order. Physicists call this causality, and it is one of the most foundational assumptions in all of science. Without it, the universe becomes logically incoherent. Effects could precede their causes. A bullet could hit a target before the gun was fired. A message could arrive before it was sent. The universe would fold in on itself in a tangle of paradoxes. Now, what happens when you introduce faster-than-light travel? Einstein's special relativity, when you examine it carefully, shows something troubling. If you can send information, or a spaceship, or any signal, faster than light, then, in certain reference frames from certain observers' perspectives, that information travels backward in time, not because anything supernatural is happening, but because of the geometry of space-time under special relativity. Different observers moving at different velocities do not agree on which events are simultaneous, and if you combine that disagreement with a faster-than-light signal, you can construct scenarios where the signal arrives before it was sent, at least from some observers' point of view. This is not a minor technicality, it is a deep structural feature of relativity, and it applies in principle to warp drives. If a warp bubble can move faster than light in one direction, and you fire another warp bubble in the opposite direction fast enough, the combined effect, in theory, could create what physicists call a closed time-like curve, a path through space-time that loops back on itself, a path that, if you followed it, would bring you back to a moment in your own past. In other words, a time machine. Now take a breath, because we need to be very careful here. The existence of closed time-like curves in the mathematics of warp drive solutions does not mean time machines are physically possible. Mathematics and physical reality are not always the same thing. General relativity's equations allow many solutions that we believe cannot exist in practice. Perfectly smooth, infinitely dense points called singularities, for instance, which the equations permit but which are generally thought to be artifacts of the math breaking down, not real physical objects. The question is whether closed time-like curves are the same kind of mathematical ghost, a feature of the equations that does not correspond to anything real, or whether they represent a genuine possibility. Most physicists lean strongly toward the ghost interpretation. Stephen Hawking, before he passed away in 2018, proposed what he called the chronology protection conjecture. The idea is elegant in its simplicity. Nature itself prevents the formation of closed time-like curves through quantum mechanical effects. The argument is that as a space-time path begins to approach a closed loop, quantum vacuum fluctuations, the same zero-point energy we discussed in Part 3, build up and diverge to infinity along that path, creating an energy barrier so extreme that the space-time structure collapses before the time loop can form. The universe, in Hawking's view, enforces its own protection against time travel, not through any mysterious external law, but through the very physics that describes the quantum vacuum. He even said, with characteristic wit, that the best evidence time travel is impossible is the conspicuous absence of tourists from the future. But Hawking was also careful to call it a conjecture, not a theorem. It has not been proven. It remains one of the great open questions in theoretical physics, a question that sits right at the intersection of quantum mechanics and general relativity, in the territory that physicists call quantum gravity. And quantum gravity, the long-sought theory that would unify the two greatest frameworks in all of physics, remains unfinished. We do not yet have a complete theory that tells us exactly what happens at the quantum level when space-time is extremely curved. And without that theory, we cannot definitively resolve the causality problem. What we do have, though, is progress. Real, tangible, published progress. Remember the paper from December 2025 that we mentioned in Part 2, the one that introduced hyperbolic regularization to warp drive geometry. One of its central contributions was specifically addressing the causality objection. The authors showed that by introducing the telegraph-type hyperbolic regularization into the mathematical description of the warp bubble, by replacing the instantaneous causality-violating features of the original geometry with a framework that preserved finite signal speeds, they could construct a warp drive model that was causally consistent, that did not produce closed time-like curves that respected the arrow of time. Now their work was purely theoretical, mathematical. It did not build anything, but it demonstrated something important. The causality problem is not an absolute barrier. It is a mathematical challenge, a constraint that restricts the space of valid warp drive solutions, but does not eliminate that space entirely. There exist warp drive geometries that do not obviously lead to time machines, and finding more of them, refining them, understanding their properties, that is precisely what the next generation of warp drive research is focused on. There is another approach to the causality problem that is worth understanding, and it comes from a somewhat unexpected direction. In 2024, a group of physicists from Queen Mary University of London, the University of Potsdam, and the Max Planck Institute for Gravitational Physics published a fascinating study. They did not try to make warp drives work. Instead, they asked a different question. What would happen if a warp drive failed? If the warp bubble collapsed, if something went wrong and the distorted space-time snapped back to its normal configuration, what would the universe detect? Their answer was gravitational waves. Gravitational waves, ripples in the fabric of space-time itself, were first directly detected in 2015 by the LIGO observatories in the United States in one of the greatest experimental achievements in the history of science. That first detection came from two black holes merging over 1 billion light-years away, and the signal that arrived at Earth was a ripple in space-time smaller than 1/10,000th the diameter of a proton. Detecting it required instruments of almost incomprehensible precision, but detect it they did, confirming yet another of Einstein's predictions and opening a completely new window on the universe. The Queen Mary team's simulation showed that a collapsing warp bubble would emit a characteristic gravitational wave signature, a specific pattern of ripples in space-time that would be, in principle, distinguishable from other sources like black hole mergers or neutron-star collisions. This is profound for several reasons. First, it means that if any civilization anywhere in the observable universe has ever used or tested a warp drive and then experienced a containment failure, we might, in theory, be able to detect the aftermath with instruments like LIGO or its future successors. Second, it gives theorists a new tool. By studying what a failing warp drive would produce, they can work backward to understand what a stable one would require. And third, it shows the scientific community taking the warp drive concept seriously enough to model its failure modes, which is exactly what engineers do when they are preparing to actually build something. This progression, from pure mathematics in 1994 to laboratory experiments in the 2010s to failure mode analysis in 2024, mirrors the development of every great technology in human history. The Wright brothers did not just build a flying machine, they studied wing warping and lift and drag. They crashed dozens of gliders. They analyzed every failure. They worked backward from what went wrong to understand what had to go right. And eventually, they flew. But there is one more dimension of the causality problem that deserves your attention, because it is not just about time machines and paradoxes. It is about something even more practical and immediate, the question of who is driving. One of the most underappreciated engineering challenges of the Alcubierre warp drive is this. The person inside the bubble cannot control it from the inside. Think about that. The warp bubble works by distorting space-time around the spacecraft. The front of the bubble compresses space, the back expands it, but the distortion is happening in the space-time surrounding the bubble. From inside the bubble, you are in a perfectly normal, inertial environment. No acceleration, no sense of motion. Everything feels still, but to change direction or to stop or to start, you would need to send signals to the region of space-time outside the bubble ahead of you. And those signals cannot travel faster than light, but you are already moving faster than light relative to the outside universe, which means your control signals can never catch up to the leading edge of the bubble. In other words, once you turn the warp drive on, you cannot steer it from inside. You cannot stop it from inside. The pilot is along for the ride with no steering wheel and no brakes. This is not a small problem, it is a fundamental one. And it is one of the reasons that many physicists, even those who find the warp drive theoretically interesting, consider the practical engineering challenges to be currently insurmountable. Not because the physics is wrong, but because a spacecraft you cannot control is not a spacecraft, it is a missile. Several proposed solutions exist for this problem. One involves pre-programming the warp bubble's trajectory before departure, encoding all the navigation instructions into the structure of the bubble itself. Another involves using quantum entanglement, that mysterious connection between particles that Einstein famously called spooky action, at a distance, to maintain some form of communication between the inside and outside of the bubble. Both approaches are deeply speculative. Neither has been worked out in satisfying mathematical detail, but neither has been ruled out either. And here is the broader point that all of this brings us to. Warp drive physics is not a finished subject with clean answers. It is a frontier, genuinely wild, genuinely uncertain, genuinely open. Every paper that addresses one problem reveals two more. Every solution that removes one barrier uncovers another. The causality problem, the control problem, the energy problem, they are all interconnected, all threads in the same enormous tapestry. Pulling on one changes the shape of the others. That is not a reason for despair. That is the very definition of a living, breathing scientific frontier. And living on a frontier, even an intellectual one, is one of the most exciting places a human being can be. Think about the astronomers of the 17th century, pointing their primitive telescopes at the sky and seeing things no human eye had ever seen. Moons orbiting Jupiter, the phases of Venus, the rings of Saturn, each discovery answering one question and raising a dozen more. They did not know where it would lead. They could not have imagined the Hubble Space Telescope or the James Webb Space Telescope peering back 13 billion years to the dawn of cosmic time. They just kept looking, kept asking, kept following the questions wherever they led. We are doing the same thing now with warp drives and quantum vacuums and gravitational waves and the geometry of space-time. We are pointing our mathematical telescopes at a frontier we cannot fully see yet, and the view, even now, is breathtaking. But there is something else happening in the world of faster-than-light physics that we have not talked about yet, something that takes a completely different approach from everything we have covered so far. Instead of bending space around a bubble, some physicists are asking a far more radical question. What if the universe has natural shortcuts already built into it? What if the cosmos, in its vast and ancient complexity, has already done the geometry for us? What if there are tunnels through space-time, connecting distant regions of the universe the way a wormhole connects two distant points in the ground that do not require us to build anything at all? Wormholes, traversable wormholes, one of the most extraordinary ideas in all of theoretical physics. And the story of where they come from and what the latest research says about whether they could actually exist is going to take you somewhere you did not expect, because it starts not with rockets or warp bubbles, but with black holes, and with the most beautiful and terrifying objects in the observable universe. There is a place in the universe where the rules break down, where gravity becomes so extreme that not even light can escape, where the fabric of space-time curves so severely that it folds back on itself, where the mathematics of general relativity, the same equations that have been confirmed by a century of experiments, reach their absolute limit and quietly stop making sense, where the boundary between what we know and what we do not know is not a theoretical line on a chalkboard, it is a physical surface hovering in space, dark and silent and impossibly dense. A black hole. You have probably heard the basics. A star runs out of fuel. Gravity, which had always been balanced by the outward pressure of nuclear fusion, wins. The star collapses inward. If it is massive enough, roughly more than about 20 to 30 times the mass of our Sun, the collapse does not stop at a neutron star. It keeps going and going until the matter is compressed into a region so small and so dense that the escape velocity, the speed you would need to travel to break free of its gravity, exceeds the speed of light. Nothing gets out. Not matter, not radiation, not information, not light. The boundary of no return is called the event horizon, and beyond it, at least according to our current understanding, is a singularity, a point of infinite density where the known laws of physics simply cease to apply. Black holes are real. We know this with certainty now. In 2015, LIGO detected the gravitational waves from two black holes merging over 1 billion light-years away, a signal fainter than a whisper that shook the entire Earth by less than the diameter of a proton, and our instruments heard it. In 2019, the Event Horizon Telescope, a planet-sized array of radio telescopes working together as one enormous instrument, captured the first direct image of a black hole's shadow. It was the black hole at the center of the galaxy Messier 87, a monster with a mass of 6.5 billion suns, 55 million light-years away. The image, a glowing ring of superheated gas with a dark center, became one of the most iconic photographs in scientific history. And in 2022, the same team turned that extraordinary instrument toward the center of our own galaxy and photographed the supermassive black hole sitting there, Sagittarius A star, with a mass of about 4 million suns, lurking at the heart of the Milky Way, roughly 26,000 light-years from where you are sitting right now. Black holes are not hypothetical. They are neighbors. But here is where black holes become relevant to our story about faster-than-light travel. And it starts with a thought that occurred to two of the greatest physicists of the 20th century, sitting at the Institute for Advanced Study in Princeton, New Jersey in 1935. Albert Einstein and his colleague Nathan Rosen were studying the mathematics of black holes, specifically the solutions to Einstein's field equations that describe a perfectly spherical, non-rotating black hole called a Schwarzschild solution, after the physicist Carl Schwarzschild, who derived it in 1916. And they noticed something strange. The mathematics did not describe just one region of space-time. It described two separate regions, connected at a single point, a throat, a tunnel, a bridge. They published their finding and called it an Einstein-Rosen bridge. Today we call it a wormhole. The concept is deceptively simple to visualize. Imagine the universe as a flat sheet of fabric. Two distant points on that sheet are separated by a vast distance, trillions of kilometers, light years of empty space. Under ordinary circumstances, the only way to get from one point to the other is to travel across the surface of the sheet, crossing every kilometer of that distance one by one. Even at the speed of light, the journey takes years, decades, centuries. But now imagine folding that sheet, bending it so that the two distant points come close together, not on the surface, but through the thickness of the fabric itself, and then punching a hole through both layers, connecting them with a short tunnel. Suddenly the distance between those 2 points is not the vast surface distance, it is the length of the tunnel, which could be, in principle, just a few meters, a few steps, a doorway from one side of the galaxy to the other. That is a wormhole, not a vehicle, not an engine, a shortcut built into the geometry of space-time itself. Einstein and Rosen's original solution was purely mathematical. It was not something they believed could physically exist or be traversed. Their bridge was unstable, it would collapse almost instantly, far too quickly for anything to pass through. And it was connected to 2 black holes, which meant that anything trying to enter would be torn apart by tidal forces long before reaching the throat. As a transportation concept, the original Einstein-Rosen bridge was interesting mathematics and nothing more. But then, in 1988, 2 physicists named Kip Thorne and Michael Morris at the California Institute of Technology, Caltech, did something remarkable. They asked a different question. Instead of starting with the mathematics and asking what it implied, they started with the destination and asked what the mathematics would need to look like to get there. They asked, what would a traversable wormhole, one that a human being could actually travel through without being destroyed, look like? What conditions would it need to satisfy? What geometry would it require? Their answer was elegant and troubling in equal measure. A traversable wormhole is mathematically possible within general relativity, but, and here is that familiar obstacle again, it requires exotic matter. Specifically matter with negative energy density concentrated at the throat of the wormhole to hold it open against the gravitational tendency to collapse. Without that exotic matter, the wormhole pinches shut the moment anything tries to pass through. The throat requires a kind of scaffolding made of negative energy to stay open. And in 1988, just as with the Alcubierre drive 6 years later, that requirement seemed to make the whole concept physically unrealizable. Kip Thorne, incidentally, is not a peripheral figure in physics. He shared the Nobel Prize in Physics in 2017 for his foundational role in the detection of gravitational waves through LIGO. He is one of the most respected theoretical physicists alive, and his willingness to seriously explore traversable wormholes, to publish the mathematics openly, to invite scrutiny, helped legitimize the study of exotic space-time geometries in a way that has paid dividends ever since. He also consulted on the film Interstellar in 2014, which depicted a wormhole with a level of scientific accuracy that was genuinely unprecedented in cinema, largely because Thorne insisted on it, and even co-wrote a companion book explaining the real physics behind the visuals. Now, for decades after Thorne and Morris, traversable wormholes sat in roughly the same place as Alcubierre's warp drive, theoretically allowed, practically blocked by the exotic matter requirement, intellectually fascinating, but seemingly out of reach. Until, beginning around 2017 and accelerating rapidly through the early 2020s, something extraordinary happened at the intersection of quantum physics, information theory, and general relativity. A new idea emerged, an idea so surprising and so profound that it has reshaped how physicists think about the deepest structure of reality. The idea goes by the shorthand ER equals EPR. Let us unpack that because it is worth understanding. EPR stands for Einstein, Podolsky, and Rosen. The 3 physicists who, in 1935, the same year Einstein and Rosen described their geometric bridge, published a completely separate paper about a puzzling feature of quantum mechanics. They describe what we now call quantum entanglement, the phenomenon where 2 particles interact and become linked in such a way that measuring one of them instantly affects the state of the other, no matter how far apart they are. Einstein famously called this spooky action at a distance, and he found it deeply unsatisfying. He thought it implied something was missing from quantum mechanics, some hidden variable that made the universe more sensible than entanglement suggested. He was wrong about that. Decades of experiments have confirmed that entanglement is real, that it is not explained by hidden variables, and that it is one of the genuine structural features of quantum reality. Two entangled particles are connected in a way that transcends ordinary spatial separation. Measure one, and you instantly know something about the other, even if it is on the other side of the galaxy. Now here is where ER equals EPR comes in. In 2013, physicists Juan Maldacena at the Institute for Advanced Study in Princeton and Leonard Susskind at Stanford University proposed something breathtaking. They suggested that Einstein-Rosen bridges, wormholes, and Einstein-Podolsky-Rosen entanglement, quantum entanglement, are not two separate phenomena. They are two descriptions of the same thing, that every pair of entangled particles is, in some deep geometric sense, connected by a microscopic wormhole. That entanglement and space-time connectivity are two faces of the same underlying reality. That the quantum threads of entanglement weave together to form the very fabric of space-time itself. If this sounds like the boundary between physics and philosophy, you are not wrong to notice that. The ER equals EPR conjecture is not proven. It is not a theorem. It is a deep and compelling hypothesis that has generated an enormous amount of theoretical work, and that many physicists find extraordinarily persuasive. But it remains, as of today, an open question at the frontier of theoretical physics. What it has done, though, is fundamentally change how researchers think about wormholes, because if ER equals EPR is correct, then wormholes are not exotic, rare objects that require special conditions to exist. They are woven into the quantum fabric of everything. Every entangled pair of particles is, in a sense, a microscopic wormhole. The universe is threaded with them at the quantum level. This connection between entanglement and space-time geometry received experimental support, cautious, preliminary, but real, from a remarkable experiment conducted in 2022. A team of physicists using Google's Sycamore quantum processor simulated what is known as a holographic wormhole. They created two groups of entangled quantum bits, qubits, and then simulated a specific pattern of interactions that, according to the mathematics of certain quantum gravity theories, corresponds to sending information through a wormhole. The signal they sent through the quantum system emerged on the other side. The researchers, led by Maria Spiropoulou at Caltech, published their results in the journal Nature and described the experiment as a probe of quantum gravity in a laboratory setting. Now, and this is crucial because precision and honesty matter, the experiment did not create a real wormhole in physical space. It simulated the quantum information dynamics that are mathematically equivalent to wormhole traversal in a specific theoretical framework. The wormhole, if it existed at all, existed in an abstract quantum information sense, not in the physical space-time sense that science fiction depicts. Several physicists, including some prominent voices, were quick to emphasize this distinction. The experiment was a simulation of a quantum gravity toy model, not a demonstration that physical wormholes exist or can be traversed, but it was the first laboratory experiment to probe the ER equals EPR conjecture in a controlled, reproducible setting, and it worked. The physics described by the theory matched the behavior of the quantum system. That matters, because in science, when a theory predicts something and you test it and it behaves exactly as predicted, that is evidence, not proof, but evidence. And evidence accumulates. There is another development in wormhole physics that deserves attention, one that connects directly back to the exotic matter problem. In 2024, physicists Remo Garatini and Kirill Zatrimailov published a paper in Physics Letters B, one of the oldest and most respected journals in high-energy physics, exploring what happens when a warp drive enters the gravitational field of a black hole. Their findings were surprising. The gravitational field of the black hole actually reduced the amount of negative energy required to sustain the warp bubble. Not eliminated it, reduced it. The presence of the black hole's extreme curvature effectively helped do some of the geometric work that would otherwise require exotic matter. The authors suggested this could be relevant for creating microscopic warp effects in laboratory settings, near compact objects, or in experiments designed to mimic strong gravitational fields. The implication is subtle but important. The universe's most extreme natural objects, black holes, might not be the obstacles to exotic space-time travel that we intuitively assume. They might be, in some sense, partners, resources, natural generators of the conditions that warp drive and wormhole physics require. The cosmos, it turns out, has been running exotic space-time geometry experiments for billions of years. Every black hole is a laboratory. Every singularity is a data point. Every gravitational wave rippling across the cosmos is a message written in the language of curved space-time, a language we are only now beginning to read fluently. And this brings us to something that goes beyond the physics. Something that touches on what it means to be a curious, thinking creature in an ancient and vast universe. When you look up at the night sky and see the band of the Milky Way arching overhead, that smear of light that is actually hundreds of billions of stars, our own galactic home seen from the inside, you are looking at a structure that is 100,000 light-years across. The nearest large galaxy, Andromeda, is 2.5 million light-years away. The observable universe extends 46 billion light-years in every direction. These are numbers so large that they resist intuition. They are not just big. They are cosmically, humblingly silencing in their scale. And somewhere in that vastness there may be shortcuts, geometric bridges connecting distant regions, woven from the same quantum entanglement that links every particle in existence. Natural wormholes stabilized by conditions we have not yet fully mapped. Space-time geometry so exotic and so rich that our current mathematics is only beginning to scratch its surface. We do not know if traversable wormholes exist in nature. We do not know if the ER equals EPR conjecture is correct in its full physical implications. We do not know if the quantum simulation at Google tells us something deep about the universe or something more limited about a specific mathematical model. These are open questions, genuinely, beautifully, frustratingly open, but we are asking them in laboratories. With quantum computers and gravitational wave detectors and planet-sized telescope arrays, with the full force of human curiosity and mathematical ingenuity and hard-won experimental skill, we are asking the universe for its deepest secrets, and the universe, slowly, reluctantly, astonishingly, is beginning to answer. The atoms in your body were forged in dying stars. The carbon in your cells came from stellar cores that collapsed and exploded billions of years before our solar system formed. You are not just an observer of the cosmos, you are a piece of it, a piece that became curious enough to ask where it came from and where it might be going. And right now, that curious piece of the cosmos is building the tools to potentially cross the void that separates the stars. That is not just science, that is the universe becoming aware of itself. But there is still something we have not addressed, something that might be the most practically immediate piece of this entire story. Because while wormholes and warp drives represent the far horizon of faster-than-light research, there is a closer frontier, one that is already being tested, already being refined, already pushing against the boundaries of what our spacecraft can do, and how we think about propulsion entirely. It is not about bending space. It is not about quantum vacuums or exotic geometry. It is about something far more immediate. What happens when you push the limits of known physics as hard as they will go, when you take the best understanding we have of electromagnetism, plasma physics, and quantum mechanics, and ask whether there is a way to move through space that conventional rockets never considered. Are there propulsion concepts grounded in established science that could get us to the stars? Not faster than light, perhaps, but fast enough to matter, fast enough to reach the nearest star systems within a human lifetime? The answer is yes, several of them. And the physics behind them is genuinely extraordinary. Let us come back down to Earth for a moment. Literally, we have spent the last several parts of this journey swimming through some of the deepest, most abstract waters in all of theoretical physics. Warp bubbles, negative energy, quantum vacuums, wormholes woven from entanglement. These are ideas at the absolute frontier of human knowledge, beautiful, compelling, and still firmly in the realm of theory. We do not yet have a warp drive. We do not yet have a confirmed, traversable wormhole. We do not yet have a way to harness the quantum vacuum at engineering scales. But here is something that might surprise you. Right now, today, in laboratories and research centers and university workshops scattered across the planet, engineers and physicists are working on propulsion technologies that are not theoretical at all. Technologies that are grounded in established, tested, peer-reviewed science. Technologies that could, within this century, and perhaps within your lifetime, send a spacecraft to the nearest star system, not faster than light, but fast enough to matter, fast enough to change everything. And the most exciting of all of them starts with something as simple, as ancient, and as beautiful as a sail catching the wind. Imagine standing on a beach, watching a sailboat move across the water. The sail catches the wind pushes the boat, and the boat moves. No engine, no fuel, just the transfer of momentum from the moving air to the fabric of the sail. It is one of the oldest forms of transportation human beings ever devised. Sails have been carrying people across oceans for thousands of years. Now imagine replacing the wind with light and replacing the ocean with the void between stars. That is the concept behind a lightsail, and it is not science fiction, it is physics. Light, despite having no mass, carries momentum. This is a direct consequence of quantum mechanics and was predicted by James Clerk Maxwell in the 19th century. When photons, particles of light, strike a reflective surface, they transfer a tiny push to that surface. The force is minuscule for any ordinary light source, but if you concentrate enough photons onto a sufficiently thin, sufficiently light sail, and if there is nothing in the vacuum of space to slow you down, then over time you accelerate, and you keep accelerating, and you keep going faster and faster with no fuel, no exhaust, no engine, just light pushing you through the cosmos. In 2016, two of the most ambitious and celebrated figures in recent science history stepped into a room and announced something that made the entire scientific community lean forward in their seats. Stephen Hawking, physicist, author, one of the greatest minds of the 20th and early 21st century, and Yuri Milner, Russian-born billionaire entrepreneur and science philanthropist, announced the Breakthrough Starshot initiative. The goal was audacious to the point of seeming impossible: design and eventually build a fleet of tiny spacecraft, each about the size of a postage stamp, propelled by laser-driven light sails, and send them to Alpha Centauri, our nearest stellar neighbor, 4.2 light-years away. Within roughly 20 years of travel time, the probes would reach speeds of approximately 1/5 the speed of light, 1/5, 20% of the cosmic speed limit. Voyager 1, launched in 1977, and now the most distant human-made object ever created, travels at about 17 kilometers per second. At that speed, it would take roughly 70,000 years to reach Alpha Centauri. The Starshot probes at 1/5 the speed of light would make that same journey in about 20 to 25 years. That is not a marginal improvement. That is a transformation of what interstellar travel means. The physics behind Starshot is real. Radiation pressure, the push of light on a surface, is experimentally confirmed and has been measured precisely in laboratories. Solar sails have already been tested in space. The Japanese space agency JAXA launched a spacecraft called Icaros in 2010, which successfully demonstrated solar sail propulsion in deep space, the first spacecraft in history to be driven by sunlight alone beyond Earth's orbit. NASA's Advanced Composite Solar Sail System, tested in 2024, successfully deployed a large solar sail in low Earth orbit, demonstrating the structural engineering required for sail deployment in space. But Starshot goes far beyond a gentle push from sunlight. The plan calls for a ground-based laser array, an enormous collection of individual laser emitters working together as a single, coherent beam, powerful enough to accelerate the tiny spacecraft to a fifth of the speed of light within a matter of minutes. The energy involved is staggering. The engineering challenges are enormous. The sail needs to be incredibly thin. We are talking about films measured in nanometers, where 1 nanometer is 1/1000th of a meter, yet strong enough to survive the intense radiation pressure without tearing, melting, or buckling. It needs to be reflective enough to transfer momentum efficiently, and it needs to be stable enough in flight to maintain its orientation under the asymmetric forces of the laser beam. For years, these material requirements seemed like the most daunting obstacle, but in recent years, researchers have made extraordinary progress. In May of 2024, a team led by Harry Atwater at the California Institute of Technology, Caltech, published a landmark paper in Nature Communications analyzing the structural and photonic design of flexible light sails. Using a sophisticated multiphysics simulator, they found specific designs for sail shapes that were dynamically stable, that would not tumble, collapse, or go off course during the brutal acceleration phase. They found that spin-stabilized sail designs, where the sail rotates gently as it accelerates, were immune to the deformation problems that had plagued earlier concepts. The paper was a major step forward in turning the Starshot concept from a beautiful idea into an engineering blueprint. Then in January of 2025, Atwater's team at Caltech published another milestone paper, this time in the prestigious journal Nature Photonics. They reported the first ever direct experimental measurements of laser-induced forces, actual light sail membrane prototypes, in a laboratory setting. Not simulations, not calculations. Real, physical measurements of real, physical sails being pushed by real laser beams. The sails were made of silicon nitride membranes just 15 nanometers thick, about 1,000th the thickness of a human hair, and the experiments measured the optical forces, the thermal effects, and the mechanical responses with extraordinary precision. Nature Physics highlighted the significance of this work in an article published in April of 2025, noting that a recent analysis had shown radiation pressure from large but realistic laser arrays could accelerate a reflective light sail spacecraft to speeds as high as 20% of the speed of light, and that such a probe could reach Proxima Centauri in about 20 years. 20 years within a single human generation, and it does not stop there. In March of 2025, a team from Delft University of Technology published a paper in Nature Communications describing light sail designs optimized using artificial intelligence, specifically a technique called neural topology optimization. Their AI-designed sails featured pentagonal photonic crystal mirror patterns with billions of nanoscale holes punched through them, engineered to maximize reflectivity while minimizing mass. The designs outperformed anything human engineers had conceived manually. The light sails of the future, it seems, will be designed in part by the same machine learning tools that are revolutionizing medicine, materials science, and engineering across every field. As of today, Breakthrough Starshot's Phase 1 has been completed. As physicist and Starshot team member James Benford wrote in March of 2026, Phase 1 successfully identified the key engineering challenges and confirmed that credible solutions exist for each of them. The program has been paused and restructured as it seeks broader support for the next phase. But it has not been abandoned. The fundamental conclusion stands: Beam-driven interstellar propulsion is not impossible. It is an engineering challenge, a very hard one, but a solvable one. Now, lightsails are remarkable, but they are not the only advanced propulsion concept worth understanding, because while a laser-driven sail could carry a tiny probe to the nearest stars, the question of carrying human beings, with all the life support, food, water, radiation shielding, and living space that implies, requires something different, something with vastly more power, something that does not just nudge a gram-scale microchip, but accelerates an entire crewed spacecraft to a meaningful fraction of the speed of light. And for that, physicists have looked at the most powerful process in the known universe, nuclear fusion. Fusion is the same process that powers the sun. Deep in the solar core, hydrogen nuclei are compressed by gravity to such extreme temperatures and pressures that they fuse together, forming helium and releasing enormous quantities of energy in the process. The energy released by fusion is almost incomprehensibly greater than anything produced by chemical reactions, the kind of reactions that power our rockets today. A rocket running on liquid hydrogen and liquid oxygen releases energy from chemical bonds. A fusion reactor releases energy from the atomic nucleus itself, from the binding force that holds protons and neutrons together. The energy difference is on the order of 1,000,000 to 1. Fusion releases roughly 1,000,000 times more energy per kilogram of fuel than any chemical reaction. Fusion propulsion concepts for interstellar travel have been studied seriously since at least the 1970s. Project Daedalus, a study conducted by the British Interplanetary Society between 1973 and 1978, designed a detailed engineering blueprint for a fusion-powered interstellar probe. The design used a series of fusion micro-explosions, small pellets of deuterium and helium-3 ignited by electron beams, to generate thrust. The Daedalus study concluded that a fusion-powered probe could reach Barnard's star, about 6 light-years away, in roughly 50 years. Unmanned, but physically realizable, at least in principle, with technology not wildly beyond what the 1970s could imagine advancing toward. More recently, the concept of fusion propulsion has gained renewed attention as advances in fusion energy research have accelerated. The National Ignition Facility at Lawrence Livermore National Laboratory in California achieved a historic milestone in December of 2022, the first ever fusion reaction that produced more energy than the laser energy delivered to ignite it. Net energy gain from fusion. This was a moment physicists had been working toward for decades. It did not instantly solve the engineering challenges of practical fusion power, but it proved the physics works. It demonstrated that controlled fusion ignition is achievable in a laboratory setting. For space propulsion, the implications are profound. A spacecraft powered by fusion could, in principle, carry enough fuel to accelerate to 10 or even 20% of the speed of light, make the journey to a nearby star system, decelerate on arrival, enter orbit, and conduct a thorough scientific survey. Not a flyby, not a postage stamp probe, a real mission, with real scientific instruments. Perhaps one distant day with human crew members. There is another propulsion concept worth mentioning, one that bridges the gap between today's technology and the more advanced systems of the future. It is called plasma propulsion, or electric propulsion, and it is already flying in space right now. Ion drives, a type of plasma propulsion, work by ionizing a propellant, typically xenon gas, and accelerating the ions electrically to produce thrust. The exhaust velocity of an ion drive is far higher than any chemical rocket, meaning it uses its propellant far more efficiently, squeezing more thrust from each kilogram of fuel. NASA's Dawn spacecraft used ion propulsion to visit both the asteroid Vesta and the dwarf planet Ceres. The Hayabusa missions by JAXA used ion engines to travel to asteroids and return samples to Earth. The technology is proven, reliable, and continuously improving. Advanced plasma propulsion concepts including magneto-hydrodynamic drives and plasma sail systems that interact with the solar wind, represent a bridge between the chemical rockets of today and the fusion drives of tomorrow. They are faster than anything we currently launch on, and they are getting better. Here is what all of this means when you put it together. We are not standing still. We are not waiting for a warp drive to fall from the sky before we take our first steps toward the stars. We are building those steps right now, from solar sails tested in low Earth orbit to AI-designed lightsail membranes 1,000 times thinner than a human hair, from laser arrays that could propel a probe to 1/5 the speed of light to fusion reactions that achieved net energy gain in a California laboratory, from ion drives already cruising through the solar system to mathematical frameworks for the warp bubbles and wormholes that might one day make even these breathtaking achievements seem slow. The journey to the stars is not a single leap. It is a ladder, and we are building it rung by rung with every experiment, every paper, every measurement, every discovery. But there is something that nobody in these conversations ever quite prepares you for. Something that lives not in the physics or the engineering, but in the sheer human weight of what it would mean to actually leave, to actually go, to point a spacecraft at a star 4 light years away and press the button and watch it go. To know that the signal confirming its arrival will take over 4 years just to reach us at the speed of light. To understand at a cellular level what it means to be a species reaching beyond its cradle for the very first time. Because when we talk about interstellar travel, whether it is a laser sail or a warp drive or a wormhole, we are not just talking about physics, we are talking about the most profound act of exploration in the history of life on Earth. We are talking about crossing the first true boundary of the cosmos. And the question of who we will be when we do it, what we will have learned, what we will have lost, what we will carry with us into that darkness, is every bit as important as the equations. And that question leads us somewhere unexpected. It leads us to the stars themselves, to what we already know about the worlds that might be waiting around them, the planets circling other suns, the atmospheres being analyzed by telescopes like James Webb, the biosignatures being hunted by a generation of astronomers who grew up watching Carl Sagan look up at the sky and wonder. It leads us to the question that underlies all of this, the question that sits beneath every equation and every experiment and every late night in a laboratory. Are we alone? If you made this far, make sure to subscribe to the channel and give this video a like, and check out this other video at the left side of the screen to keep exploring the wonders of the universe, the absolute limit of human travel through space. Why are 99% of the universe's 2 trillion galaxies forever unreachable despite any technology we invent? I will see you there. Thanks for watching.